Hi, so welcome back to this next little bit on state machines. So you can see a little animated GIF going here. This is from XKCD. If you're not familiar with them, then I would suggest that you go and have a look there. They're great places to spend a bit of time, laugh at some of their jokes, okay? The reason I put this up is because I want to talk about how you really need to be able to make systems reactive and responsive. And although this is a funny GIF, a hilarious one, because you've got all sorts of weird lights doing all sorts of strange things, some traffic light systems are actually fairly complex, multiple lanes, multiple sensors, and they have to be able to react and respond to different queues of vehicles, queues that are empty, queues that are getting too long. All these sort of things must come into the system. And of course, they vary at different times of the day, on public holidays and on weekends. And so the system needs to be quite reactive and responsive to many different things. And so traffic lights are actually really common sort of ways to use state machines to think about how a state machine works. So I'm just going to give you a very simple traffic light. We're going to look at a very simple system where we've got cars going from east and west, so crossing each other, and then we've got north-south, and then of course we've got pedestrians. So this is a very simplistic set of traffic lights. We've just got the three systems, okay? And then of course our initial state is going to be cars in the north-south direction can go. Now I've got three different expressions of a state machine here, using three different ways of coding it, and that's what this is really all about. We can use a switch case, we can use an if and else if, or we can use the one that I've already explained, which is the while. And there's just subtle differences, but no real benefits between either of them, because in actual fact, your compiler may well turn them all into exactly the same code anyway. So it's just up to you as to decide which one of these three you might like. I've used this one here for the state machine designer, which is part of my simulator. But of course, if you used a switch case, for instance, initially state that variable is set to the value ns, which is 1. So what happens is it switches, it's looking for case ns, north-south, and then it does this. It checks to see if the pedestrian switch is pressed, and then it brakes and jumps back around to this while loop. Again, state is still north-south, so it jumps down here, does this, and then continues in this pattern until something happens. And the only if statement I've put in here at the moment is the one for the pedestrian switch. But obviously, after a period of time, it would need to change to east-west. Again, this is exactly the same. It's exactly the same implementation as a switch case. First of all, it checks to see what the state is. It finds out that state is north-south, does whatever's in here, and then continues around the while loop again. And will continue to do this flow here until the state changes, okay? Now, the subtle difference with the while loop is that it will start here, state will be north-south, so it will come down here, and it will stay in just this loop here until the state changes. So it won't change from that, okay? Now, that's a subtle difference in the expression of these, but how it's actually coded, as I said, by your compiler is up to the compiler to figure out, and that's fine. So this is just whatever's usable for you, but I've used this one as the example. But these do exist and you can code them this way. Now there's a fourth way, okay, and that is using function pointers. And we're not going to go into function pointers in state machine design, but for those of you who have an interest in this or come back to it in the future, here's a couple of really good references to it, okay? Now, what I want to do next is I want to have a look at a particular implementation of a state machine, just to look at some of the issues around state machine design. So what we've got here is we've got a straw inserted into this little pipe, and the idea is that you use this as a way of detecting to see if you've got excess alcohol. Now, the way it does that is through a breath test, obviously not a blood test. So what happens is you blow through the straw, and you have to blow hard enough and long enough for the alcohol sensor to get a good reading, okay? Now, the way we control the long enough and hard enough blow is that inside this little plastic block is a little P, like a whistle in a referee's or a P whistle. And when you blow this through here, some of the air escapes up here, and some of the air causes the little P to rotate around inside here, which gives you that warbling type sound. So I'm going to show you exactly what this sensor is like. So let's come back down here, and I will just get this camera set up and go out of stop my screen share. Okay, and we'll just have a look at this device. So you blow in air through this direction here, and it comes into this block. And what's inside this block is a little P, which can rotate around. Okay, so it can rotate around like this, and the air comes up through this hole. Some of the air will go past here and will cause the P to rotate around. Of course, if you don't blow very hard, then the P will go slowly. And if you blow hard, the P will go really fast, okay? And if you don't blow long enough, then the P won't do too many rotations, okay? It will just come to a stop after a short while. Now, as the P is rotating, what happens is we have an infrared transmitting LED, which is on one side plugged into this little hole in here. And so it's plugged into this little hole here. And on the other side of that, we have a sensor. And so as the P rotates around, it will break the sensor, okay? You can see that that's what will happen, right? And so this is how we determine whether a blow is long enough and hard enough. To determine if it's long enough, we count the number of rotations. And to determine if it's hard enough, we can calculate the speed of the rotations. And if the speed's below a certain level, we want it to flag that it is not a good blow. And if there are too many rotations, then we again want to flag that it's not a good enough blow. So now I'll just go back to screen share again. And we'll tilt this back up. So what we've got is we've got a state machine. Well, first of all, let's start with the block diagram. I've got this little tiny 85 microcontroller. It's very, very similar to the 80 Mega 328P, except it's only got a few of port B pins on it. You can see that some of them are analog to digital pins, and many of them are just ordinary I/O pins. And it's got I've connected an opto switch, which is basically the infrared transmitter and receiver, and the P little ball rotates around in between it. We have three outputs: a good blow, a bad blow, and an okay to blow system. So let's go down and have a look at the state machine and have a look at some of the things that we might want to consider when we're designing a state machine diagram. So we've got our states. Initial state is state weight. Here we're doing a count to 30. I'll just pop this back on to annotate the spotlight. So here's our state weight, and here's our state count to 30. And then we've got a state where we're monitoring the count to see if it's how hard they've blown or how many counts have taken place. And then we've got read the alcohol. So the only time we want to read the alcohol level is if it's been okay. So the first thing we do is we clear these two LEDs to say that it's neither good nor bad, and it's okay to do a blow into the machine. And then when the trigger happens, like you start to blow, immediately it transitions out of here. It gets that first pulse and transitions out of here into this state where it starts to, it needs to start counting and doing things here. And when you've got 30 counts, we turn off this okay to blow. But when you've got more than 30 counts, it comes down here and calculates the speed. And then it determines that actually the speed is low or the speed is high. And if the speed is low, it flags to say it's a bad blow, and makes sure that the good blow LED is off and we're stuck in the state. And then it will transition somehow. Will cause a transition to this state here. So we need to put some stuff in here. Also, if the P count is greater than 400, that means that we've got quite a good amount of air and it's blown it for long enough, then, and of course the speed is okay, then we can come in here and do the alcohol read level, okay? So now there's a few things about this state machine that we really need to have a think about because there's some problems with it, okay? Let's have a look at this and see if we can figure out some of the issues with the state machine. Some of you will be thinking about it immediately, and some of them will come to mind quite quickly. If we detect P movement, we come into this state, but the only way out of this state is if we get a count of greater than 30. But say, for instance, someone knocks the machine and it just rotates the little P in the system a couple of times, then it's stuck here, okay? And it's actually, it's turned off our LED that it's okay to blow. So that's not good enough, okay? So there must be a better way of thinking about this. We want 30 counts to go down here so that we can start monitoring the speed. But maybe actually we don't want 30 counts. Maybe just want one count and we start calculating the speed. You know, there's a certain amount of problems like this. Maybe we would start a timer at this point in time and then say that actually if we haven't got to 30 counts of the P rotations before the timer times out, then actually we need to just go back to the system here again, or we need to flag a bad blow or something like that. So you can see as you start to unwind these problems in designing the system, then you can actually get a good idea of how the system works. And the reason that I use state machines, and they are used widely in industry, they sort of go back to a guy named Harrell, H-A-R-E-L, who was he was doing some software design for a jet fighter for the landing gear of it. And he had drawn up these big diagrams, and they were standing around looking at them about how the landing gear should work. And a test pilot came by and looked at the diagrams and the information and said, no, it doesn't work like that. It needs to work like this, 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 and this. And between them, they actually worked out how the system should work. And what they came up with was basically this sort of type of diagram, a state machine diagram. And it was from there that the software was developed. You could just turn this automatically into code. But this whole concept is really powerful because it allows you to bring in other people who are not software experts, but who are system experts. They might know nothing about software, but they can look at this diagram and you can walk them through it, and then they'll say, oh no, it needs to work like this. What if this doesn't happen? You know, we've seen this happen before, and all these sort of considerations can come out. So you don't have to be a software expert to do this design, actually. And this is part of a design language called UML, Unified Modeling Language. State machine diagrams are one of the diagrams there. So you can bring experts in to help you design your system and think clearly about the problem long before you look at the code. So in this case, you don't have to start coding. You can just use my simple state machine designer to generate automatically code for an AVR. But there are many of these tools around as well. So that's one of the problems, is that if we don't get enough counts, should we actually revert back to one of these two states here after a period of time? So, but when we do get to 30 and we come down here, we can see that the speed is less than 10, we get a bad blow, and the P count is greater than 400. But these are two different things. So again, we're sort of left with this idea of what happens if this P speed is greater, but the count is lower. Okay, so we might get a really short, sharp burst, and then the speed would come up here. But if the speed was good enough, but the count was also at 400, which way would it go? And this is a really important part of state machine design, in fact, software design overall, because in this case, it's non-deterministic. This design cannot distinguish between which one of these is best and which one it should take first. So that's a really important situation, because your P speed might be low, but your count might be high. That would be okay. But what happens if there are different ways out of this state that are really, if this P speed gets to 400, but the speed is still low, it'll still show as a good reading. And so there's all sorts of complexities here that I want you to think about in your mind about how would you resolve these if you were designing the system. And of course, in the assignment, you're required to design some systems, not this one. Also, both of these states here automatically transition back to this state without any delays or anything at all to say, hey, something's happened, because this would set the bad blow, and then it would come up here and immediately clear it. So you would never see it, and it would be just sort of saying, okay to blow again. So we need some way of monitoring and controlling when this transition takes place. We need a condition in here of some description. What would we make this condition conditional upon? A period of time, so that there's a good indication, maybe a beeper going off. We could add all sorts of features to our system. And of course, again, also once we've done a positive read of the alcohol, we need to display the alcohol level. But before we go back to the main system, we need to perhaps wait for a little while, okay? So you can see that there's a couple of issues here around transitions that have no conditions. That's a problem, okay? Here, you can get stuck in a state and there's no way of exiting it, okay? Because not all conditions are covered. And down here, we've got a determinism type issue where we've got conditions that one could happen before the other, when really everything is still okay and should go here, it goes here, or it goes here and should go here. So because we're monitoring different things, we've got this non-deterministic sort of understanding, and it's a bit random actually what can happen. And randomness is not part of our system design, okay? Everything must be deterministic and not random. So this is a sort of introduction to these sort of problems, okay? And I'll just break this video here and I'll come back in the next one. Cheers.